Welcome, everyone. Thanks for joining us. We will be discussing a new integrated LED driver design today that's able to deliver full power to a light in 500 nanoseconds or less. We think this presents a remarkable development for machine vision, as this advanced driver design promises new possibilities for improving the performance, precision, and repeatability of high-speed imaging systems. But before we dive into the details, I'd like to begin with some important context for this development. First, it's important to define our terms, or at least acknowledge that they are sometimes hard to define. The meaning of high-speed imaging, for example, may seem self-evident in the context of machine vision, but the term has no fixed definition independent of a particular application. It simply means that an imaging system can capture relevant data accurately and repeatably, whether that be a packaged product whizzing by an inspection station, an automotive crash test, or the capture of falling snowflakes in broad daylight, as this image shows. Capturing snowflakes requires high magnification and a small field of view to see the minute details. The field of view is about 1 inch here. Yet the system is required to capture snowflake images with winds up to 70 miles an hour. Imagine the speed of a snowflake passing a 1 inch field of view at 70 miles an hour. This requires a shutter speed in single-digit microseconds to freeze the motion and prevent blurring. Saturating a camera image in microseconds requires extremely bright light. In this case, so bright that the light from the LED source within the field of view drowns out the ambient photons from the sunlight in the background. So how do we apply this to machine vision? Engineering a high-speed imaging system demands several design considerations beyond what conventional machine vision applications require. Those considerations include camera trigger latency, how field of view influences shutter speed, and calculating the exposure times necessary to freeze rapidly moving objects in time. But tweaking the camera provides limited results. Widening the aperture of the camera will help it capture more light, but this decreases depth of field, which can be problematic in some applications. Similarly, increasing camera gain can brighten output, but also amplifies image noise. Proper illumination, however, is another term more easily defined within the context of an application. It requires more than simply applying enough illumination at the correct wavelength or angle. As shutter speed increases, the target needs to be more brightly illuminated to ensure proper exposure at each pixel. Given the limited number of ways a camera system can be tweaked to gather more light during short exposure times, it is advantageous to pulse the light source to illuminate objects of interest more intensely. Traditionally, xenon strobes or pulsed LED light sources have been the favored solutions for freezing part motion in high-speed imaging applications. Xenon strobes are brighter in terms of absolute photon output, and their light pulses, when strobed, typically last from 15 to 30 microseconds, though they can pulse as low as 250 nanoseconds if necessary. To date, the shortest pulses that conventional LED lights can effectively deliver are in the low microsecond range. But faster is not necessarily better. In contrast to xenon lamps, LEDs offer a number of advantages, including greater ruggedness, lower maintenance, and longer lifetimes. LEDs also emit within a narrower spectral range than xenon sources. This tighter spectral control can be used to enhance the contrast and visibility of key features in an image. As solid-state light sources, LEDs can be overdriven to provide higher intensities versus constant operation. This involves pulsing an LED at higher current for a brief period and switching it off for a specific rest time. As power increases, this provides diminishing return in output, however. LEDs are typically overdriven at 4 to 10 times the rated currents to provide 3 to 8 times the rated output. In extreme cases, 10 times or more the output is possible. The comparatively compact form factor of LED lights is also another benefit. It enables them to be positioned closer to the target. Applied to light, the inverse square law states that intensity decreases in proportion to the square of the distance. This decline, relative to the working distance, permits smaller LED heads positioned closer to the target compared to xenon lamps. In practical terms, this means they can achieve comparable or even better illumination at the target compared to xenon sources. Last but not least, LEDs provide better control over the duration, intensity, and shape of each pulse. This is very important in machine vision because the absolute intensity of a light at its source has less bearing on image capture than the flux density created at the target, the number of photons per unit area projected within the target field of view per 1 second of time. The key is not the absolute intensity of the light source, but how many photons it can deliver to the target some distance away. A vision system's ability to freeze motion in an image is a function of how precisely and quickly it puts photons to the pixels. The faster the motion, the more challenging this becomes. A common goal is for each pixel of a camera sensor to detect one point on an object. If the point is moving too quickly relative to the camera's exposure time, it may be captured across multiple pixels. The resulting pixel blur causes poor image data. The best image quality will limit pixel blur to 1 pixel or less, although this level of performance is not always necessary. High-speed inspection applications often specify the allowable threshold for pixel blur, and vision engineers design systems accordingly. Traditionally, engineers use the following formula to calculate the minimum exposure time required to avoid a specified pixel blur. Pixel blur equals line speed times exposure time times the image size in pixels divided by the field of view. Assuming that pixel blur can equal no more than 1 pixel, for example, it is possible to calculate exposure time by plugging in other known quantities. In this example, if the engineer knows the line speed is 3,000 millimeters per second, the image size is 1960 by 1080 pixels, using the pixel counter in the direction of travel, or 1960 horizontal pixels in this case, and the camera's field of view is 100 millimeters, then this formula works out to an exposure time of 17 microseconds. This means to keep our image sharp within the desired 1 pixel, we must have a 17 microsecond or less total exposure time. Given the limited number of ways in which a camera system can be tweaked to gather more light during short exposure times, it is advantageous to illuminate the object of interest more intensely. As pulse lengths decrease to accommodate shorter camera exposure times, the shape of each pulse, the time it takes the LED to reach full intensity and then switch off, becomes increasingly important. Measured in intensity over time, an LED pulse should exhibit a square shape, which indicates that the die is achieving full output power more quickly. This ensures that the LED is still not rolling on when the camera shutter opens, but is illuminating the target with full intensity. This ensures that an LED is not still rolling on when the camera shutter opens, but is illuminating the target with its full intensity. Otherwise, pixel blur can begin to creep in. Conventional LED systems designed for high-speed imaging can deliver pulses in the same microsecond duration using external controllers. Importantly, however, the physics of such systems introduces inescapable latency issues that dull the edge of the square pulse shape. The longer the cable, the greater the impact from the latency. Even a 1 or 2 foot cable connecting a driver and light source will impose significant parasitic impedances that contribute substantially to system jitter and extend the rise to full intensity. Integrating the driver and controller in close physical proximity to each other on an LED motherboard eliminates the need for external wiring and ensures that high current pulses from the driver are delivered directly to the LED across comparatively short, impedance-controlled printed circuit board traces. Smart Vision Lights took such an approach with the development of its NanoDrive driver to minimize resistance and parasitic electrical losses from external cables. LED lights featuring this technology are thus capable of quickly delivering tens of amps directly to the LED die to achieve full power in 500 nanoseconds or less with comparable shutoff time. Applied to high-speed imaging, such light sources permit incredibly short image acquisition times and precision timing that would be impossible to achieve using LED sources driven by external controllers and wiring. LED lights, powered by this advanced new driver technology, can be configured to enable sub-microsecond pulse edges and to maintain 1 microsecond pulse widths. With overdrive enabled for extreme brightness, even at a 10% duty cycle, such configurations are capable of 100,000 strobes per second. Additionally, faster on and off rates help compensate for latency issues during asynchronous operation, wherein a camera shutter is triggered by an external source, such as an approaching product tripping a photosensor. For all the sophistication underlying built-in LED drivers capable of pulse edge resolutions measured in nanoseconds, the end benefit is simplicity. A competent vision designer can apply complex trigger schemes, expensive cameras, or software tricks to optimize image capture at extremely high speeds. Such solutions, however, always face the headwinds of an end user's cost-benefit analysis. By enabling shorter, brighter pulses characterized by on and off times in the nanosecond range, integrated LED drivers will boost both accuracy and throughput for high-speed inspection applications. Importantly, the greater control that they afford will also help streamline the design, implementation, and cost of these systems. In conclusion, integrated LED drivers can provide the following benefits: performance and accuracy that can't be matched when compared to using an external controller, easier integration of machine vision solutions and expanded options for applications that require rapid image acquisition, plug-and-play ease of use while still achieving the highest performance results, reduce cost and complexity. I and Smart Vision Lights would like to thank you for your time in watching this presentation. We hope you found the information useful and enjoyed it.